All right. So there's an idea of something called a sample space. Not final space, sample space. And all a sample space is a collection of all the things that could happen. That's what it is. So when I talk real slow, it's like a good note to take if you want to. It's up to you. So for example, if I was picking a card out of a deck of cards, well, would it sort of suck to write that sample space? How big would that sample space be? 52 big, right? I'd have to put ace of clubs, two of clubs, ace of diamonds, two of diamonds. There's a heart. Oh, shit, right? But that's what a sample space is. It's just a listing of all the things that could happen. All right, so here's a fun one before I answer that question directly. This is so fun, kids. Just be ready. Let's say I had, let's not use the letter G with 6. Let's say I had 4 red, 6 blue, and 2 green poker chips. Just to be so creative and original. Oh, I hope that heat turns off. And let's say I picked 2 of them. What would my sample space be? So can somebody tell me one thing that could happen? Beautiful. Red, blue. Right? Not red versus blue, but red, blue. And then you just keep going. And if you're kind of systematic about it, you're not going to leave anybody out. How big will this set be? Now watch how you can figure out. I'm going to pick 2 chips, right? How many options are there for the first chip to be? You do this. What's different about each chip? They have a different color maybe. How many colors are there? 3. So when I pick the first chip, there are 3 things it could be. When I pick the second chip, there are 3 things that could be. So for every one of these, there's 3 of these. So 3 times 3 is 9. So I know the sample space is going to have 9 things in it. So it would be red, blue, red, red, red rum, no, red, 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 green, and then it would be
Blue, red.
blue. Well, let's be systematic about it, right? Blue, blue. Do you see what I'm saying? Blue, red, blue, green, and then it would be green. We could do it. We could do it. Green, blue, green, red. It doesn't really matter what order it's in, but if you're systematic about it in some way at least, you're not going to leave anybody out. Now this problem says this. Thought I could remember and I forgot. There are 12 total books. 8 are fiction books and 4 are nonfiction. The fiction books are numbered 1 to 8. So great titles. Well, this is a good read. 7. That's a good read. Oh yeah, don't look in the box. So fiction books are numbered 1 to 8. Non-fiction books are numbered 1 to 4. So when I reach in and pull out a book, give me one thing that could happen. You got to be more specific, right? Because the fiction books are numbered 1 to 8, and the non-fiction books are numbered 1 to 4. So I reach in and pull something out. What's one thing that could happen?
2 non-fiction.
Beautiful. I can get non-fiction 2. How do you think I would represent that here? Non-fiction, I'd probably put a N for non-fiction. And then if we want to do this in order, I could say non-fiction 1. Keep going. That's all I'm going to do on that problem. That's number 36. Not a hard thing. You just list all the things that could happen. I have 12 books. They are different types of books, fiction, non-fiction, and they are numbered 1 through whatever. So when I reach in, what could I pull out? List all the things that could happen. Don't start getting in non-fiction 3, fiction 2, non-fiction 8. Holy shit, you're going to forget somebody. Do it in order. You guys with me? That's all a sample space is. Just tell me all the shit that can happen. I like it. Okay. Anything else from homework stuff? No? You guys doing all right? I'm a math teacher, so I'm used to making people angry and sad. It's horrible. What a great life I've chosen for myself. All right. So, let's see. What else? I think the last thing we did was we talked about me getting slapped on both cheeks. Remember that? And if you weren't here last time, you're like, you got to slap him? That would have been great. No, it wasn't you guys slapped me, thank God. And that was related to what to do with an and. So can somebody just tell me, and is basically what, or is basically what operation? Can you guys do that? Or is basically doing what operation? Addition. I love it. And why does that make sense? Because or should make things bigger. So I'm going to add in more possibilities. And is basically multiply. And this is apparently the sign language for multiply. I don't know. You guys with me? And why does that make sense? And should make things smaller. And when I multiply things less than one, they do get smaller. So on a really fundamental level, those operations make sense with each one. So let me remind you guys. Why do I keep saying basically? Not because that's my favorite word, but what is the formula for probably of A or B? Aw, poor little dude. That didn't go far. All right. What is this formula? Probability of A plus probability of B minus, no? Yeah. So on one level, it should hopefully make sense. If I count everybody in A, and then I also add in everybody in B, I've counted anybody in both twice. You with me? If I counted all the women in here, and then I counted all the Republicans in here, and added those together, why does that by itself not really make sense? Because there are some women who are Republican. I would have counted those people twice. And depending on your leanings, maybe you want the vote to count twice. But too bad. Stop. So, or is basically add. What's the formula for and? I think this is one of the last things we did. Anybody remember what that formula was?
PB.
PB.
Minus B.
Times.
P A given.
P A given B. And you're ready for this? It also works the other way around. Because A and B is the same thing as B and A. All right, if I said Tom and Sue, and you're like, Sue and Tom, shut up. Same people, come with me. So Ann doesn't care which way it is. All right, maybe. Ooh, if you missed last class and you haven't watched the video yet, you want to, you missed a lot. We did a lot. Were you here last time? We did a lot. Remember that? We did a lot. Okay. Let me see. So, I don't think, I can't remember if we actually did some examples using this idea yet. So let's just do some, because some of you guys are like, I don't know what the hell you did. So let's do some examples using this dude here. Get out of here. I think we might have done it, but it's good still to do this, because I think I did talk about independent versus dependent. Does that sound familiar? Well, at least one person says yes. So, okay. So let's say, is anybody, all right, how are cards set up? Cards, they have ace, 2, 3, up to 10, and then what? Jack, Queen, King. And so this is how many total cards in that one suit? 13, right? Because King is like 13. Ace could be high, but let's just say it's low. It doesn't matter, all right? We're not going to play poker. Don't get excited. So there's 13 cards. How many suits are there?
4.
4 suits. So each suit looks just like this. So there are spades and clubs, and then hearts and diamonds And then I always think about Lucky Charms when I'm saying this stuff. But it's no balloons or anything like that. Okay. Horseshoes? No. That's the only guy I love how some of you guys like stick to this stats. Okay. So there's 13 spades, 13 clubs, so forth. There's like a 10 of hearts, there's a 2 of diamonds, so forth. I think most of us know cards. Okay, maybe. So, let's just start with, if I picked one card, what's the probability it's a king?
1 out of 52.
Say again?
Is it 4 out of 52?
Yes. You guys, everybody see that? There's 4 kings, a king of each of these, out of 52 total cards. And that reduces to 1 out of 13, and whatever it is decimal. Okay, now, stay with me. If I pick 2 cards, there are 2 ways to pick 2 cards. I could pick a card and then put it back in and then pick another card. Or I could pick a card and throw it away or feed it to my little brother and then pick another card. Now, why are those 2 different from probability standpoint? What happens if I pick a card and throw it away before I pick the next one?
Check from the denominator.
There's going to be how many cards left?
51.
51. So like you said, the denominator is going to change. So we call the one where I put the card back, we call that with replacement. Because we're not very creative in naming things, right? We put it back, replaced it. Right. So if I pick 2 cards with replacement, what's the probability to get a king and then another king? Okay. So we know the formula for this. It's fundamentally multiply. So let me see if I could just do this problem, and then I'll point out where the formula comes into play. So I've got 2 things I want to do, right? So I'm going to put 2 spots here with times in the middle because and means times. What's the probability the first card is a king?
1 out of 13.
Yeah, 4 out of 52, right? We can make it 1 out of 13. But we'll put 4 out of 52. I'll put that card back in. What's probably the next card is a king? 4 out of 52 still, right? Nothing changed. I kind of reset before I did the next pick. And then whatever that is. It's 1/13th, 1/13th, 1 out of 169, whatever the shit that is. You guys maybe have calculators. You could even help me out, but if you wanted to. Like, we're not going to help you out, Matt. Boy, do it. No, I'm done. And then let's do another one just to see. What's probably I get a king? Let's say something else. Let's probably get an ace and then a 2. This one's a little boring because is it going to be something different? How many aces are there? 4 out of 52 times another 4 out of 52, right? In fact, any cards I put there, there's 4 of them. Okay. And that's still going to be 1 out of 169, which is whatever it is as a decimal, whatever the hell it is. All right, stay with me. Everybody with me a little bit? So if I picked 3 cards, what would change about what I'm writing here? If I wanted 3 kings, I would have had to put... How many spots do I have here? 2, because I was picking 2 cards. So if I wanted 3 kings, if I picked 3 cards, I would have needed 3 spots. 1 more spot for the 3rd dude, right? So I always think of this first step as like a hangman game. You draw in lines for how many things you want to do. What do you put in the middle? Times. Why? Because it's freaking and. Okay, now here's where the formula really comes into play. And it came into play here too, but it's easier to see over here. So what if I do this without replacement? So I pick the first card and then I throw it away. And my little brother still goes and gets it and eats it because now he's dependent on plastic. Sorry, Jim. So what's the probability now that I get a king and then a king? So So there's still two things I want to do. Still times in the middle because it's and. First card I pick, everything's normal. I pick that card, what's probably is a king? 4 out of 52, and then I throw it away. So now what's probably the next card is a king?
3 out of 51.
Beautiful. I lost a king just now, right? And I lost a card. So one less king, one less card. If I had another freaking king, 2 out of 50. Why didn't this one change? Because I put the damn thing back in. So you got to really pay attention to if I say with replacement or without replacement to know which situation you're in. Okay, maybe. It kind of makes sense. If I lose something from my group, my denominator at least is going to change because I've lost one thing. Okay, what about this one though? This one gets a little more interesting, thank God. Probably an ace and then a 2. Well, probably the first one's an ace is still 4 out of 52. Throw that away. What's the probability the next one is a 2? 4, 2 still, but 51 cards. And then whatever the hell that is. Did everybody see that? Why did that one change? Because I lost a king and that's what I wanted. Why did this one not change? I still got all my 2s. It's an ace I threw away. Now watch this. The formula officially, remember the formula was probably A and then B. Probability of A times probability of B given A, right? That's exactly what we're doing here. What is this? That's the probability I get a 2 given that I already picked an ace. That's why it changed. So that is what the formula says to do. It's just, again, easier to not try to do this directly. You can actually work it out because you can count. Again, I know how many cards there are. I can count. Anytime I can count what's going on, I'm less dependent on the formulas. It's my hopeful Tai Chi. Oh, okay. Let me see. Something else I left out. Oh, I might as well do that too. Yeah. All right, one last thing, and then I'm going to shut up for a while, give you guys a worksheet to try out. Help me out. Look at this. So, how many cards are there total? 52. So, would you say this is a very large population I'm working with? 52? Is that large? And you're like, dude, I don't know what large is, man. Large is thousands or something, right? 52 ain't much for a population. That's small. How many Americans are there at the moment? I forgot to look this up, but it's 360 million maybe, something like that. Something around there. I remember the day that it became 300 million, and man, we added 60 pretty quick. All right. So, what the hell has it got to do with it? If I said that 11% of Americans are left-handed, and I want to say, what's the probability I get if I pick 3 Americans? What's the probability that I get exactly 1? Get out of there, Jeff. That's not me. What's probably the first one's left-handed, and the last 2 are not left-handed? Is that cool? You guys see what that means? Left-handed. It wouldn't really be right-handed. It would just be not left-handed, but screw it. We're just using an R for not left-handed. You guys with me? What's probably I pick 3 Americans at random, and the first one is left-handed, while the last 2 are not. That's the question. Doesn't this feel like exactly what we're just doing? I'm going to have 3 spots, right?
How do you know if you're multiplying?
Oh, how do I know I'm multiplying?
Yeah.
So if I pick 3 people, I want the first one to be left-handed. And oh shit. Okay, good. So and is the word that's very often hiding.
Okay, gotcha.
Because I have multiple ways to represent and. Or is going to be like, or is going to show up, and it can't just hide somewhere. Okay, I like it. I like it. Maybe. Okay. What's really nice, what's going to come up later even more in your face is in algebra. What's it mean when I have multiple variables is standing next to each other? That means what operation? Ha, holy shit. Yeah. And it matches with statistics because it would have an and in the middle because it wants all those things to happen at once. Still multiplication. Thank the gods, right? Whatever deities like. Let me see. All right. You still with me? Somebody does this. Don't write this down. This is bad. Green for go, but don't go. 11 out of 100 times, what do you got to put? 89 out of 99 times 88 out of 98. All right. Do you kind of get the idea here? If you write this, what are you assuming? That there are only 100 Americans, right? That doesn't explain traffic. And we're just in San Diego. So obviously there's not just freaking 100 Americans. You would have to make it out of 360 million. But now watch. Stay with me now. Stay with me. If I had something out of 360 million, and then I took one person away, that would become 359,998,000. Does that change relatively much? You could do this. I love you guys. Why did I have to do it here? Somebody help me out. Get a calculator. What's 4 divided by 52? You can do it.
0.0769.
0.769. Okay. What's 3 divided by 51?
0.0588.
All right. Now look. Did that change much? Did that change much? You can do it. Yes, it did, didn't it? I mean, that's a decent amount of change. Oh, holy shit. Because 52, if I take 151, that's a big change. But 360 million, if I had $360 million and a dollar fell out of my pocket, I might not even waste the time to bend down and pick that bad boy up. Oh, okay, who cares, right? If I got 52 bucks total to my life and a dollar falls, I'm on that thing. Get away from it, right? You guys understand? So, what the shit does that mean? When our population is huge, we do not have to write fractions. Get out of fractions. We can just work directly with the probability itself. Left-handed. So what's the probability this first guy is left-handed or girl?
0.11.
0.11. What's probably this one is right-handed? If that one's 11% chance of left-handed. What's probably they're not left-handed? Who? 89. And then you got another 89, right? Because you got another not left-handed. All right, maybe. Yes?
Are we replacing them?
Say again?
Are we replacing them back?
Replacing what?
The person?
No, we're not.
Why did that number change?
So you ready? All right, help me out. Somebody help me out. What is 11% of 360 million? Help me. You got a calculator. I'll do it. Let's see. 36. So it'll be 39, 6. I think it's this.
Yeah.
All right. Sorry. Step it up. You got calculators. Should be quicker than me. So that's 11%, right? So there's 39,600,000 out of 360,000,000 left-handed people. Let's say I take one of them. So let me check with you guys. What is this divided by this? Freaking that, of course, because that's where it came from. Are you guys with me? Everybody with me? All right, let's take one person out. So now this is going to be 39. Let's just assume even this changes. Out of 359,999,999. Let's do that division. Help me out. Do it. You can do it. Some guys are like, I came here, man. That's all you're getting from me. All right. Eddie?
0.109.
Yeah, but keep going, right?
999.
0.10.
9. There's 6 9s and 7.
All right. How would you say this to another human being? 11%. Do you understand what I mean now? That if I have a very large population, a large ass denominator, and I take one away, that ain't doing shit to the value. If I have a really small population, look how much that sucker changed. Big time. Would you rather have a 7.7% chance of dying in a surgery or a 5.8% chance of dying in a surgery? Yeah. This one, who gives a shit? They're both 11. Okay, maybe. Who had a...
I don't get why we use .89.
Okay. You ready? Watch this. If there's a 10% chance of rain today, what's the probability it's not going to rain? If there's an 11% chance of a left-handed person?
Oh, that makes sense.
Okay, thank you. Right? Two opposite probabilities have to add to be one, because together they cover everything. I like it. I like it. So, you just do this. This is awesome. So when do I have to set up fractions when I have a small population? And I'm going to make it really clear. It's never going to be like, is 200 small? No, I'm going to make it like in the 50s at most and then in the millions. So it's really clear. I have to do it this way when I have a small population. And I can just use directly the percentages when the population is huge. So if I'm talking about everybody in Germany, well then shit, I can just use percentages. What's this here? It's like,
713.
yeah, 0.087. 1. So watch this. Let's do another one. Let's say the probability of somebody drinking beer is 0.79, and I pick 5 people. What is this question? I haven't really shown you this. This notation, I think the book uses a stupid little, screw that shit. This means not drink beer. What would that be? These drink beer, these don't drink beer. What would that probability be? 0.21. All good, because then together, that's everybody. So what does this question mean? The first 4 drink beer, and the last one don't. So how many spots am I going to have? 5. It's crazy. They're going to be separated by what operation? Multiplication, because this is an and. Drink beer, and drink beer, and drink beer. So what's the B here? It's going to be...
179.
So 9 times... So 9... Can't we just do this? 0.79 times 0.79 times 0.79 times 0.21. I got 4 that drink beer, bam, and 1, I don't really need that beer, but still, 1 that doesn't. And then whatever the shit that is. Okay. All right, and I think the, again, whatever, I don't know what that is. 6.48, 0.32. See what it is? Do it again? Do it again?
0.0817.
Okay. Well, that's neat. I wish I could say that I made that on purpose. All right. So before I give you this worksheet, just in case you suck at keeping notes, here's the formulas we've gotten so far. Gosh, oh my, are you a good green marker? Good, no. You're a bad one. Are you a good one? Let's do it this way. Now, it's funny. These are good to have in your notes. There will be problems where you have to use these formulas. Most of the problems on the sheet I'm about to give you, you shouldn't. I think we talked about that before, right? You're not used to hearing a math person say this. But remember, we developed the formulas after we calculated probabilities. We just looked back to see what we did. I don't know if you guys remember that. So if I have a situation like a table or something, I don't know, where I can count all the stuff, I do not need the formulas. In fact, very often somebody will use them incorrectly and make the whole problem much worse than it should be. All right, with that said, let me give you this little handout. I'll tell you one thing. I want you to work on the side that says probability worksheet. And you can work together if you want to. The other side is a practice quiz. It's the only practice quiz I'll give you, because what's the next thing we're going to take grade-wise? The double quiz. It's officially set for Monday, right? We're going to push that back to Wednesday, because obviously we're a little off kilter with Jeff's horrible memory. So, everybody with me? The double quiz is a week from today. Okay, I like it. Here, you guys, once I get these passed out, if you need to borrow a calculator, come up. Once I get these passed out, let's see if everybody can. Again, work on this side that says probability worksheet. That's the one we're going to go over together. We got to do stupid house. Yes. I'm sorry.
I'm fine.
Oh, no.